Okay, so we are in this book here, Generalized Linear Models with Examples in R, Chapter 1, and we are on question 1.6 here, okay? And in 1.6, we're going to be actually using some R code, and so if you're going to use this Colab sheet or make a copy of this Colab sheet or do anything in Colab with R, make sure that you come up here to Runtime, go to Change Runtime type, and this is normally set to Python, and so you want to make sure that it's on R if you're using R. Okay, so we're going to load some data called turbines from a package called GLMsData, and briefly the data gives the proportion of turbines developing fissures after a given number of hours of runtime. Okay. And then we have a bunch of things we need to do with them. So I won't read those, we'll just kind of tackle them as we go along. So the first thing is you need to install and then load the package. Okay, so that's what we're doing here. And then we need to load the data that is contained within that package. And so I've done that here with the data command. And then so I don't have to type out turbines every time, I just assigned this data frame to be D. Okay. So we can even see what D looks like here. Oops. I'll run that, and that's what D looks like. There's our data frame for D. And we have three variables: hours, turbines, fissures. Okay. Okay, so the first one is use the names command to determine the names of the variables in the data. Okay, well, we kind of just looked at that already, but we have hours, turbines, fissures. Okay. Determine which of these variables are quantitative and which are qualitative. Okay, so we could just we could do that in a couple of ways. Like I said, we already saw the whole data set, and they're all numerical. They're all integers, in fact. Okay, so they're all quantitative. Okay, but when you get a really big data set and you want kind of a summarized view, you can use the structure or str, and then pass in the whatever thing you're trying to get the structure of. And this gives you how many rows, right? 11 rows or observations with 3 variables or 3 columns. Okay, and we have the columns are hours, turbines, fissures. They're integers, and then it gives the first few values of each of those. Okay. So in other words, all of the variables are quantitative. Okay, they're all integers. Number 3 is for any qualitative variables, define appropriate dummy variables, but this isn't applicable because we don't have any qualitative variables, so we can just skip that. Okay, so now we want to summarize each variable. So I can come here and I can use the summary function. This is one way to do it. Okay, and now for each of my variables, I get a minimum, I get a mean, okay, I also get medians, and first quartile, third quartile, I get a maximum. You could also get things like the standard deviation and the variance, so maybe I'll do that here. So I could get like the standard deviation. Well, I don't think that'll work actually, but I can get the standard deviation of D hours. Okay, and it's this. Okay, and I could do the same for what were the other ones here? Turbines, although that's a count variable, well, it doesn't matter. And so it's 14.7, and I could get the standard deviation for fissures, D fissures, right? So D fissures, okay, and whatever other summary variables that you wanted. Okay. So now we want to use R to create a plot of the proportion of failures. This is turbines with fissures, so a failure is a fissure, I suppose, against runtime, and runtime is actually hours. Okay, so so the first thing is that we don't have a proportion, right? What we have in our data is we have turbines and we have the number of them with fissures, but a proportion would be fissures divided by the number of turbines. So first we have to create that variable. Okay, so I'm going to append a column to my data frame. I'm going to call it prop fail for we're going to call it proportion of failures. Okay, and so I can do it in a few ways, but I'm going to use the with command. So with the data frame D, divide fissures by turbines. Is that right? Hold on. I think that we want turbines, the number of turbines. Yeah, no, that's right. Okay, I was confusing myself. Okay, so now we have this variable, that's the proportion of failures, okay? And then we're going to plot it, so I'm going to plot prop fail, the variable we just created, against hours with data D. Okay. And here we have our plots, okay, or a plot. So number 6 is which features are important. Okay, well, this is a pretty open-ended question, but there's a couple of things. One is that at least within the range of, I guess, 0 to what, like 5,000 hours? What's the biggest? So 4,600 hours. There's a relationship that's basically looks more or less linear, okay, for the proportion of failures. So that's interesting. But since the y-axis is actually a proportion, right? Proportion of failures is a proportion. This linearity won't last forever as we go on and on and on, because we expect that this apparent line will start to asymptote as it gets to 100% failures, right? We can't go above 100% failure. Okay. Yeah. So number 7 is, no wait, let's see. Yeah. So number 7 is, would linear regression be appropriate? So probably not, for the reasons I was just stating, which is the y variable here, the outcome variable, is a proportion. And so even though it looks linear here, it won't be linear forever. It will start to asymptote. Okay. And then finally, number 8, this was confusing me. I put it in a code box rather than a text box, but this is 8 here. So we're supposed to read the help file for the data frame turbines, okay, and determine if the data came from an observational or experimental study, then discuss the implications. Okay, so to get help on well, anything, on a function, but here we have a data set, if there is a help function, or if there is a help file available on it, I question mark turbines, and we pull up information on the thing that we're asking about, okay? So we need to figure out if this was observational or experimental, and right away it says, in an experiment, ... So this is an experiment, okay? And then, so what are the implications of this being an experiment? Okay, well, one of the things that it tells us, assuming that, we don't know how the experiment was ran, but let's just say it was with proper methods and everything. One of the things that it tells us is that the variables that we have here, right, that these are the relevant variables. These are all of the relevant variables that we need. And so, so we can trust, trust is a weird word, but we can trust that, we can trust the inferences of our regression, at least insofar as we've made the appropriate assumptions with our regression. For example, our regression would probably be fairly trustworthy within the domain of hours here, right? So from 0 to 460 or whatever, or 4,600, and assuming similar stresses being applied to the turbines, etc. Okay, but in other words, there probably aren't missing variables here that would somehow confound our interpretation of the data.